So we did our project on Kepler and his laws of planetary motion, and we related them to the concepts that we learned in our dynamics class. Kepler's first law is also known as the law of ellipses, and it talks about the path that a planet will follow in its orbit around the sun. Previously, it was thought that planets moved in a circular path around the sun, but Kepler found that they actually move in an elliptical path with the sun located at one of the foci points of the ellipse. Since this path is elliptical and not circular, it means that the distance that the planet is from the sun is constantly changing as it moves in its orbit. Kepler's second law is called the law of equal areas, and it talks all about a planet's speed during orbit. The planet's speed is constantly changing in orbit since there's not an equal distance to the sun throughout the orbit. The faster the planet moves, the fastest, the closer it is to the sun, and the perihelion is the point that it would move the fastest because it's the closest point to the sun, and the aphelion is the farthest point from the sun. This law describes that the area that a planet will travel over the time that it takes to travel that area is equal throughout, and that is the aerial velocity. So the aerial velocity is constant while a planet is in orbit around the sun. Kepler's third law is also called the law of harmonies, and it talks about the distance the planet is from the sun and relates it to the period. The square of the period of orbit is directly proportional to the cube of the semi-major axis. So basically, this means that the time for a planet to orbit the sun will increase as the size of the ellipse increases because the radius is increasing. So the photo there shows that the farther the planet is from the sun, it will have the longer period. And for all of Kepler's laws, there was an unknown force behind all of these motions and distances and paths. And Newton later described this about 20 years later as the gravitational force.
So the big part of what our project was deriving Kepler's second law. And to do that, we had to use certain dynamics principles that we learned throughout the semester. So these include the conservation of linear and angular momentum, angular impulse, angular velocity, and differential area with cross product. So as you can see here are a few snippets from the derivation. So the first snippet shows the conservation of linear momentum with angular impulse involved. And then you see the radius times the perpendicular component of momentum. And then later on, we see angular velocity start being included. And then we can see the differential area, and then we divide it by the differential time in that. And then you start to set certain equations equal to each other, and you eventually get this equation, which is dA over dt equals L over 2m, which is constant, which is basically just reiterating that that aerial velocity stays constant throughout that elliptical orbit.
Okay, what I did here was I used a blanket, a wooden egg, and like some marbles to simulate a gravity well. And when you throw the marble around the blanket and it circles the egg, it simulates like a planet orbiting the sun. And you can see as it gets closer to the egg or the sun, it like I don't know if you can see in here, but it spins faster. And yeah, that's all I did. And it was fun doing this. It took like 20 minutes, but yeah, I was glad it worked.